I'm trying to set up my screen just to share. Can you see?
Yeah, I see.
Is it just the title screen or is it the notes and the title?
I see title screen and then Denny Crib proving. Is that part of the title?
That's good. That's just
Okay.
the slide. Yeah. I just want to make sure you're not seeing the presenter view, right?
Sure. Oop. My Zoom decided to close. It crashed on me. Wonderful. I'm going to give it about a minute or two and then get started. All right. So hi all. I'm Cooper Lebo, and we got a wonderful speaker, Dennis Krug, to talk about improving software design with everyday things. Without further ado, Dennis, take it away.
Okay, thanks, Cooper. I appreciate it. And welcome to everybody. And thank you for joining us today. And today, as Cooper mentioned, we're going to talk about software design, but from the perspective of what can we learn about how to do it by looking at everyday things. And if you look at just that title or that concept, you may be wondering, well, what does software design have to do with everyday things, right? Well, to answer that question, I want to talk about where this talk came from. And this talk originated after a book club that I participated in last year. Along with a group of improvers here at the company, we read through this book called The Design of Everyday Things. And each week we would meet for about 30 minutes to discuss what we were learning and how to apply that to what we were doing each day. And this book, I had not heard of it at the time, but it is apparently quite famous in the UX world. Its author, Don Norman, is a cognitive scientist, and back in the late 80s, he published this book under its initial name, The Psychology of Everyday Things. But he joined Apple Computer in the early 90s as a user experience architect, and that was one of the first times that the language, the user experience was part of a job title. And around that time, there was growing attention towards user experience, but it wasn't until 1995 that Don Norman is actually credited with coining the term UX to describe this whole field. And The Design of Everyday Things is really his seminal work, which was, again, published in the late 80s. And what it contains is his analysis of common objects that we interact with throughout our days to get tasks done. And through that analysis, he produces and brings to the surface some ideas and concepts of design. And by studying those, we can learn what makes for good design and what makes for bad design. So let's start by thinking about some of the encounters that you may have had with everyday things. Think about office building doors. Have you ever pushed hard on an office building door trying to escape the cold weather only to discover that it pushed back and you have a jarring response that pushes you almost to fall backwards? And in that moment, you realize, I should have pulled this door instead of pushed it. Or how about in your kitchen? Have you ever fired up the stovetop burner, only to see an open flame sprout up right next to the pot that you had just filled with water? Or how about a faucet? When you've been traveling, let's say a hotel sink or bathroom, have you ever singed your hands with scalding hot water, and as your arm flew backwards to escape the pain, you realized, man, I must have somehow turned on the hot water when I thought it was cold? Or maybe you have fumbled around in the dark outside of your front door of your apartment after a night out, trying to figure out which key to use to open the door, how to hold that key, and whether or not those teeth are supposed to be faced up or down in order to insert it into the lock. Or what about batteries? Do you ever scramble to find new batteries, wrestle with the cover to a battery compartment, jam them into a TV remote, and hastily begin pushing in numbers, try to get to your favorite show, or maybe kick off just in time, only to discover that that remote was just as ineffective as it was just moments ago when it had dead batteries? And almost certainly you found yourself standing in front of a bank of light switches, flipping switches indiscriminately back and forth, trying to find the one switch that activates the room or activates the light in the back of the room. So think about how you felt as a result of each one of those experiences. Did you feel silly or stupid, or most certainly you felt frustrated, if nothing else? But why did these events occur? For the office building doors, why did you push instead of pull? And how come you turned on the wrong burner in the kitchen? And why didn't you know how to select cold water instead of hot? And for keys and batteries, how did you have trouble inserting batteries properly or unlocking a door when you've used these devices your whole life? And for light switches, why did you feel that need to flip switches back and forth without any knowledge or indiscriminately, trying to figure out which was the right light to turn on? Well, there are actually reasons for each of these. For the doors, turns out that the architects and the building designers were so concerned with the visual appeal of clean lines that they didn't bother to consider the thousands of people that would be coming in and out of those doors, many of them first-time visitors who would need to know how to operate those doors. They didn't leave any visual indicators on where to operate the doors, much less whether to push or to pull them. And for stovetop burners, the manufacturers are so concerned with placing control knobs away from potentially hot surfaces that they didn't consider how people might determine which knob pairs with which burner. And for the faucet, hotel brand designers were determined to create a modern look for their bathrooms. So they created a sleek looking, novel shaped faucet to put in every room in order to set their brand apart. They didn't consider that many people from all over the world would visit that room in a different state of mind for different reasons. And now they'd be required to learn how to use a faucet unlike they'd ever seen just to get hot and cold water on demand during their stay. And for keys, the conventions in our culture are so deeply rooted that people do not even consider that it ought to be more common to have keys and keyholes that support insertion in any direction. The technology actually exists, but many manufacturers just disregard it. And similarly with batteries, manufacturers of battery-driven devices are so widespread and unaffiliated that attempts to standardize these and make for compartments that can tolerate battery insertion in whichever direction have failed miserably. In addition to this, often producers and designers of such devices, of battery-driven devices, are engineers, and they design them to be logical, and they expect their users to do the same. And for light switches, the home builders and commercial developers who are responsible for installing these nondescript banks of light switches don't consider the eventual end users like homeowners and conference room attendees who will have no prior knowledge of the lighting configuration. So they simply use the cheapest and most common building materials available. Through realizations about everyday things like those, several core ideas emerge in Norman's book. The first is that it isn't your fault. So those feelings of being foolish or silly or stupid are not yours and yours to own. It's actually bad design that is at fault. And the reason that there's bad design is because the needs of people are often overlooked. People are often left just to compensate. So for instance, on office building doors, people may tape large handwritten notes that say push or pull in this area. Or you may have to memorize which burner pairs with which knob. Or you might place labels underneath light switches in a conference room to indicate which light pairs with which part of the room. So there are lots of ideas that are covered in the book, The Design of Everyday Things. I'm just going to cover 3 of them that I think we can apply to our design efforts when it comes to software development. The first idea that Norman introduces is that of the gulfs of execution and evaluation. And the concept is that as we move through our days, we have goals to accomplish tasks, and we have to interact with the things in the world to achieve those things. So anytime we have something we want to do, we start with that goal. It might be to enter the house or to pay a utility bill. And we need to interact with the devices through their designs to achieve that goal. So we'll have to interact with a lock and key to open the door. We may need to interact with a web browser and the internet, and maybe the light bills website's payment portal in order to pay our light bill online. The concept is that there's a gulf that exists between that goal and the world, and that can be divided to 2 facets. The first is the gulf of execution. And this is where a person tries to figure out, how does this thing operate? For instance, where is the keyhole? What direction do I need to hold the key? Or online, where do I sign in to get to the payment portal? And also things like, can I push the door open now? Does the key turn, right? And then there's the gulf of evaluation on the other side, the second half. And this is where you evaluate, as you interact with that device, what occurred, and is this what I wanted? So is it what I expected? When I turned the key, did the lock turn the direction I expected it? Can I push the door open now, and have I actually achieved my goal? Or when you log into a website, do I see somewhere that I can click on to get to a payment portal? Where can I enter in my account, my banking information to make that payment? So the role of the designer is to try to bridge these gulfs for the person using the device or the system. So we have some tools that Norman covers or introduces to help us to provide, to answer those questions in those 2 gulfs. The first tool he covers is what he calls an affordance. And this is an indication of what can be done with the device or thing. So in the everyday thing realm, we look at an office chair, and we can see how there are some bars along the sides of that chair. Those are probably a good place to rest your arms. So there might be an armrest there. And you can also see that there's some wheels along the bottom there, which is a pretty good indication that the chair can be moved. So these are indicators, visual cues of what can be done with this device. In the software world, we might have a button that's labeled sign in, giving us a clue that, oh, there's some way to access some privileged features for this application. Or there's maybe a contact us link. So we know that somewhere the system supports the ability to reach somebody at the company. Or we'll have a menu that will give us an indication of the kinds of functionality that's available to us. The second tool to bridge the gulf of execution is what's called a signifier. And rather than being an indication of what can be done, this is an indication of where a thing can be done, some form, some operation. So on an everyday thing example, we look at a pair of scissors, and it's pretty clear where we want to put our hands here and where we would put paper or the item that we want to cut. Further, it's pretty obvious here where to put a thumb versus your fingers in this on the handle. So it gives us a good idea of where to operate the device. If we look online, we often have a form, and we might have placeholders in our input fields to tell us where to enter in specific kind of information. And then we also have control buttons that are labeled to tell us what can be done. So we know exactly where to click here to cancel out of an operation or to proceed forward and submit. Another tool we can use to help bridge the gulf of execution is constraints. These are the things that limit the attempted operation. An example of this in an everyday world might be emergency exit doors. These doors only move in one direction, and that is outward from the building. So they cannot be opened from the outside to support entry from the inside, right? There's really only one very simple place here to operate this door, and that's that bar right along the middle. There's only one thing you can do with it. You can't pull on anything here. You can only push it outward. So there's a constraint that's been used there to fit the designed purpose for this door, which is to be used only in emergencies. And for a software application, we see examples of this in a drop-down list where we'll have a list of limited choices available. So we only select from one of those available. We also see example of this when we disable a button. That gives us a clue that, oh, this form cannot yet be submitted because it's invalid. So we block a user from moving forward until the constraint is met that all valid information has been provided. Another tool we can use to bridge the gulf of execution are mappings. These are an indication of which controls operate which system parts. We see an example of this on many car seats in automobiles. Motorized car seats, they often have a layout and shape that matches the seat itself. So it's very easy to look at this control panel and determine which part of the controls will slide the seat forward and backward, and which part of the control may adjust the backrest. The equivalent on the software side might be something like a table where we have a list of data in the system or objects in the system, and we have controls in line with each one of those rows of data to tell us which controls will perform that action on which object in the system. And then a tool that we have to help bridge the gulf of evaluation is feedback. This is where the system somehow communicates the results of user interaction and status to that user. So on the everyday thing example, consider a coffee maker. Coffee pot, of course, will start empty. When we turn it on, you might have a LED indicator showing you that it's on and that the burner is hot potentially. So you have that visual feedback. There's also some audible feedback that happens just by the nature of as the coffee pot begins to brew, you can hear it brewing. And then once a coffee maker is done brewing a pot, there may be a loud beep or something to indicate that it's done with its work and you can pour coffee from the carafe. On the software side, we often see a disabled button and maybe a spinner, letting us know that the system is working on the request to submit a form. Maybe on in a car, an example of this would be the blinker, the arrow that shows up on the blinking arrow that shows up on your dashboard mimics what's happening on the blinker light on the exterior of your car when you turn the blinker on to turn one way or the other. And then on the software side, we see things like notifications that'll tell us there's an alert or something that we need to tend to. And then there's one tool that helps users bridge both the gulf of execution and the gulf of evaluation. And that's what Don Norman calls the conceptual model. And he describes this as a simplified explanation of how the system works. An example of this could be the accelerator and the brake pedal in your car. A driver of a vehicle does not need to know exactly what happens when they press the gas pedal or the accelerator pedal in order to make the car go. They just need to know that one pedal is going to make the car go faster and the other pedal is going to make the car go slower. This is particularly relevant in today's world where we have the emergence of hybrid and electric vehicles. A driver can step into any kind of car and still know how to operate that vehicle because they have the highly simplified explanation of how that system works that they carry with them. In the digital world, an example of this might be the file and folder system that we use on our computers. Digitally, there's no such thing as a file folder or a file, but this helps us understand how information is stored, very similarly to how files might be stored in a file cabinet in the real world. So when we put these tools together to help bridge these gulfs, we get the elements of good design. And the key characteristics of good design are discoverability, which allows users to easily know what's possible and how to use the device or system. And we get understanding. Users can understand the system well enough to be efficient and effective with it. Another topic covered throughout the book is a review of relationships between humans and the machines we interact with. Take a look at some of the characteristics that describe these two and their operating environments. And let's think about these in the context of the strengths of the human. So let's start at the top and consider creative and imaginative. Well, humans are very creative and imaginative. They're capable of solving complex problems and making connections between seemingly unrelated things. And the results of human invention and creativity are everywhere, from the laptops that we're using to connect today to art galleries and even the concerts and light shows that we go and view for our entertainment. Creativity is very evident in humans. And they are full of common sense. We carry all the experiences and knowledge with us each day as we move through the world. This is the thing that allows us to travel to other countries, to drive on roads we've never seen before, and maybe to order from the menus of restaurants we've never visited. We're able to use that prior knowledge, the knowledge and the memories of the prior experiences we've had to approximate what the food will taste like. But when it comes to retaining knowledge of systems data, we start to falter a bit. We might remember what we saw in specific systems yesterday. For instance, a bank account yesterday, maybe we remember exactly what our balance appeared as yesterday. It's unlikely we're going to remember all the transactions we viewed yesterday when we saw those details. Or it's unlikely we're going to remember exactly everything that we saw in our email inbox yesterday. And humans are definitely not mechanical and precise. For instance, we know how to use a date capture field, but it's much easier for us to mentally just picture or envision a date, or maybe we see a calendar in our head. Or another example, we can connect to power adapters, or we can connect power adapters and USB drives and things of these nature to our laptops. But sometimes it takes us a few minutes to figure out which direction the adapter is to be plugged in, right? So it's slow, and we can understand it well enough, but it's kind of painful to try to remember which adapters go with which device. And it's usually a slow and tedious process to actually make those connections. And then when it comes to handling interruption, even though we are often interrupted during our days by text messages, conversation, it makes us quickly forget what we were doing or maybe what we wanted to say if we were interrupted in conversation. So we lose focus fairly easily, and there's plenty of research to show how crippling to our productivity this can be and how it can introduce mistakes at work. But now let's consider those same characteristics from the aspect of the strengths of a machine. If we look at creative and imaginative, well, a machine is not creative and imaginative at all. Unless it's designed into the machine language or the artificial intelligence engine within the software of the machine, it doesn't have any creativity, and most of them follow simple, rigid rules of behavior. The machine is certainly not full of common sense. Again, any kind of common sense behavior would have to be programmed into a system. It would have to be something that's designed in the system to make approximations to represent the idea of having common sense. But when it comes to knowledge of system data, it has everything. So anything it's been programmed to store could theoretically be available to the system. And being mechanical and precise is the very essence of what a machine is. If you tell a machine what to do and when to do it, it will do it, right? And it will store those results in a table column that's been assigned a data type to declare exactly how many bits may be used to represent that data. So it's extremely detailed and extremely precise. And as for handling interruption, aside from hardware failure, this won't occur. In fact, many machines can and are designed to handle interruption explicitly. So if we were to approximate and draw out the strengths of a human with respect to these characteristics, and then do the same for a machine, it might look something like this. And so if we bring these two together with these offsetting strengths in mind, we can achieve a complete coverage of all of these characteristics. And the big idea is that if we design, that we should design for collaboration between these two. So knowing what we know about humans and knowing what we know about machines and their capabilities, and being fully aware of the strengths of each, we can employ that in our designs to make sure that those offsetting strengths are utilized to produce the most effective and efficient tools for humans. Now, the software development industry is traditionally poor at this, often blaming software problems on user error. But the reality is that we haven't really considered the reality of what people using software products need. So I'd like to go through some of these and give some ideas on how we might, as software developers, design our systems to help create this complementary system of collaboration. Let's start with handling interruption. Instead of forcing software users to follow a very specific series of steps, we can create our software in a way that permits the user to supply or complete any step in any sequence, and then simply verify it before it goes out and is submitted, right? It could go through a final check process. Again, to help people handle interruption, let's preserve the work that they are working on, especially for predictable events. So instead of disregarding a partially completed form when a session times out because someone had to walk away from their desk, let's record the partially completed form continually and then pre-populate it whenever they're able to return to the system. Let's also help them recover after the effects of some distraction, the adverse effects of some distraction. So instead of relying on a modal dialogue to protect data, where somebody might mindlessly answer yes, and then realize, oh, I did not actually want to remove that data. Instead of that, let's offer a recovery option. Knowing that this could happen, we can introduce an undo action, or we may have a more complex scenario where somebody realizes days later that they have misconfigured something and they wish to restore the configuration to what they had days ago. Well, we can introduce that to the system knowing that that's a possibility. And as for being mechanical and precise, let's design our software in a way that allows for the user to dictate how they want to provide that information. So instead of requiring dates to be entered in a very specific manner, let's have a date field that just collects a date and gives them options. And we can program our system to interpret a reasonable set of options that they are likely to provide. And then knowing that people sometimes have typos, instead of allowing the entry of years that are nonsensical, let's warn the user when we notice entry like that and request verification that they really do want to enter in something that seems like an anomaly. And then better yet, when it comes to dates, let's avoid date capture unless it's necessary. So instead of having a form where the date is always captured because we know it's required field, let's pre-populate that field to something by default that would allow them to move more quickly through the form. Or if we have a date range entry, for example, we could say in a scenario where it's optional to have an ending period to specify, maybe we conceal that capture of that second field unless the user indicates to us, yes, I do want to actually specify an end date to my period. That way we can just produce and put in front of the user one field for the majority of cases where they only need to enter in the one value for the date. And how can we capitalize on the fact that the system has knowledge of the entire breadth of data? Well, instead of relying on a user to remember exactly where to see certain figures in the application, we can make the state of those numbers immediately accessible. So instead of just displaying a bank account here, for example, let's display the bank account and the balance that most typically is desirable to be seen with that information at the time. And if there's questions that we know someone will want to answer when we have a warning case or an anomaly, for instance, if we know a user is going to want to know, well, what is the balance when the balance is unbalanced? When the ledger is unbalanced, or when was the last time it was in balance? Instead of just publishing a notice that there's an unbalanced ledger, let's give them the context that goes with that. Tell them, try to answer those questions up front, and then allow them to go digging for details should they want to investigate further. Let's also notify users of important events. So instead of leaving it to users to discover missing work, in this case, the context is that some configuration needs to be completed by a different department. Well, let's design the machine to notify that department immediately to complete that configuration before it's eventually needed for actual task later down the road. And when it comes to notifications, let's make sure that we streamline notifications and make them context aware and filter the actionable messages by user role or activity to make sure that our users are not bombarded with a large number of tasks that's overwhelming. Another thing we can do is we can notify why the system has a current state. So instead of just disabling a control that we know the system should not support based on certain system state, let's offer the user an explanation on what's happened. In this case, we're telling the user that the fiscal year cannot be locked until all of the periods within that year are closed. And let's also leverage humans' common sense as they work with the software. Let's rely on system standards and shared human experiences to decide how to design and display things. So for instance, on error messages, instead of displaying a cryptic error message that the program understands, let's tailor that message to something that informs a user what happened and what they might be able to do about it. And then also, let's use conventions to expedite the user experience. Instead of trying to differentiate your brand by creating an application layout that is different or novel, let's stick with conventions and place controls where people expect to find them. And likewise, if we have messages that indicate system failure or success, let's follow conventions on color coding, on how to display that information, again, to streamline the ability of users to understand the system and what its current state is. And then let's also leverage the ability of humans to be creative and imaginative. Let's rely on that ability. So instead of leaving a user stranded with important information, let's display that information right away. Collect it from the system, display it all in one place, and give them something with which they can move their process forward with. And also, let's present the information from the system in a way that helps to foster insight. So instead of just dumping data from a database directly to the screen in a table, just because it's stored in that manner, let's display information using visualizations that allow humans to make those connections, spot trends that they're able to see much more quickly than a computer would be able to be programmed to find. So the final area of focus from the design of everyday things that I want to touch on is designing for error. And this is something I know that I was convicted in as a front-end developer. I know that I've spent a lot of time designing and developing for the happy path or the best case scenario. The book reminded me that often we can anticipate there are going to be errors, and we should make sure that our software not just accounts for that, but accounts for that in a way that helps people achieve whatever task using your software for. So the ideas in the book on how to design for errors, number one, is to use constraints to limit the occurrence of errors in the first place. So this would be things like making sure a form cannot be submitted to your server from a front-end application until you know that you have valid data that's been captured. Also forcing users to make choices prior to exposing the related selections. So cascading menu types of user interfaces are useful here to guide the user towards what kinds of things are relevant to avoid error in the first place. Another area of challenge is to view errors as an approximation of a task. So the advice in the book is to make the assumption that an error is simply an approximation of a task. So assuming that the task is partially complete when the error occurs. So the example here might be, let's say a form is submitted to a server and does have some errant information. Maybe it was something that could not be detected until the system examined all of the system knowledge that it had from other clients. And then it determined maybe there's a username conflict or something of that nature. Take, for example, a large form, maybe a registration form. And on that registration form, you have a username that you've requested to use. Well, if that username is already taken and it's been taken up very recently during your population of the form, you may have provided all the other information about your profile correctly. It's just the username that can't be used because you'll need to specify another one. Well, the suggestion here is to design your software in such a way that the system simply asks for the one piece of information that is incomplete. That would be the username, right? Rather than forcing the user back to the entire form, risking them changing the data on that form in a way that would invalidate it, just help them with that final piece that they need in order to accomplish the overarching task of register me. And another suggestion from the book, a reminder, is to always make sure we let our users know when it is us versus them. So if it's a technical failure of some kind that the user can do very little about, we should report that. If it is them, then we need to tell them exactly what they can do within the system in order to complete the task. And then lastly, as in some of these other cases, when conveying a message, we want to think about how to provide guidance on recovering from this error, whether that be resubmitting or providing an additional piece of information. We want to make sure that we're telling the user exactly what the system will need to help them complete the process. So the key takeaways from this book and how it relates to improving software design is, number one, the role of a designer, and that's us as we design and develop our software, is to consider the needs of people. The challenge here is to stop thinking of our customers as users, just software users, and to start thinking of them as people just like us who experience many of the similar frustrations with other people's software systems that we know we have control of avoiding in our designs. And so we're challenged to actually make this happen in our own software products. The second is to use these tools of good design to help bridge those gulfs of execution and evaluation. And those are the tools that will help us address number one. But to do that, we need to consider the context of our people, what they need, and what environment they're actually operating our software in order to determine the proper need. The next thing is to think about, how do I design my software for collaboration between human and machine? And here again, we want to remember, what are those limitations of humans and the machines, and how can we best put them together in our software products to have each compensate for the other. Some of the summary items there, supporting flexible user input, making the system state and reasons for that state obvious to system users will help. And then backing up user entry until it's discarded explicitly or it's submitted to the system can also help. And lastly, we want to make sure we design for error. Main thing here is to expect and report all errors. And then we want to make sure we report those errors in a way that guides a user towards recovery. And this idea of considering errors to be a result of a partially completed task, I think is particularly interesting to think about the back and forth between client server and how we might be able to make that more efficient and cleaner and faster for users to collect simply the extra information we might need that the system has reported is errant. That's a wrap. I hope that you have found some of the lessons learned through the design of everyday things and its analysis and looking at it through the lens of software development and design. I hope you found that as interesting as I found them. And I encourage you to try to apply these ideas in your software product. And if you have any questions, I'm welcome to take those now.
Appreciate you taking your time out of the day to give us this informative speech. I, for one, don't focus enough on UI development, so I appreciate the information. Hopefully I can take something back and actually be a better UI developer. But I appreciate it, and thank you all for taking the time to listen.
Yes, I echo that. Thank you for joining today. Appreciate your time and have a good day.